Unit 4 Chemistry, Chapter 15, Part 2. Our second type of organic molecule are the carbohydrates. So carbohydrates have got significant amounts of carbon, hydrogen and oxygen, and this is our general formula. Okay? So C to the X, H2O to the Y, which basically means however many oxygens you've got, you're always going to have twice as many hydrogens. They can range from relatively small molecules, molecular masses somewhere between 100 and 200. Glucose, for instance, which we're going to look at in a lot of detail, has a molecular mass of 180. But they can link into huge polymers, which have got molecular masses greater than 1,000,000 grams per mole. The smallest are monosaccharides. These ones tend to be polar because they have lots of polar OH groups. The largest are the polysaccharides, which are the polymers made of the monosaccharides. Okay. So some examples of monosaccharides are here. The most important one we're going to look at is glucose. Okay. Monosaccharides can link together to make disaccharides. You can put two of them together. So glucose and glucose gives you maltose, but glucose and galactose gives you lactose, which is found in cow's milk and some people are intolerant to. If we link them together to make polymers, you'll see all of these are polymers of glucose, which is why glucose is the most important one, okay? For a variety of different uses, depending on how it's arranged. Okay? So glucose is used for energy, it also makes polysaccharides. You guys can look up the energy content of these in your textbooks to see just how much energy there is in each of them and do a comparison of those. Okay. Fructose, very similar to glucose. It's actually got exactly the same molecular formula, but as you can see, this one's got 5 carbons in the ring and 1 sticking out. This one's got 4 in the ring and 2 carbons sticking out. If you link those two together, you make sucrose, which is used to transport around plants because it's much less reactive than either of these. What's not a similar structure, but it does behave similarly in your mouth, is this one, aspartame, which is an artificial sweetener. Okay? So your task is to look up the energy content of each of these and compare which one has the most energy per mole. Now, if we have a reaction of 2 monosaccharides, they're going to undergo a condensation reaction. The reaction is between the OH groups of the adjacent molecules, and we make an ether link. Sometimes you'll see this called a glycosidic link, but we need to know the ether functional group anyway, so you can use glycosidic, but it's safest to use ether, because all glycosidics are ethers. Glycosidic is a subgroup of ether, which is specific to carbohydrates. However, not all ethers are glycosidic. You can have an ether link in something which is not a carbohydrate. So here, if we link 2 glucoses together, we are going to be linking this OH group and this OH group here, which for some reason is not showing up, and we are going to make this maltose, and here we go carbon, oxygen, carbon, so there's our ether link. Okay? We can do the same thing with fructose, and again we are going to make an ether link. Polysaccharides are made when we have those reactions happening over and over and over again. Okay? And the 3 most important ones are starch, glycogen and cellulose. Starch and glycogen are both made from alpha glucose. Okay? Cellulose is made from beta glucose. Now they're very, very similar, but they are optical isomers of each other. And this one here, so here we've got a chiral center, and there we've got an OH group sticking up instead of down. That's important because it means that the cellulose ends up straight. It also means that this group here sometimes sticks up above and sometimes below. Okay? So how that impacts on the structure? Well, starch can end up with branches. Okay? It actually has 2 components. It's got amylose, which is straight chain, which actually ends up making coils, and a myelopectin, which makes branches. Okay? Glycogen, similar to a myelopectin, but much more highly branched. which is important because at the end of each of these, this is where we can break it down. So it's a much more readily accessible energy source. And this is used to store energy in animals, who generally need to access their energy more quickly than plants who use starch. Cellulose is entirely straight, okay? And what you'll see in cellulose is that, see how this got CH2OH? In starch, it always sticks up the top. In cellulose, it goes top, bottom, top, bottom, top, bottom, which means we've got these groups sticking out which can form hydrogen bonds between them and make a really strong structure.